Today I'm going to focus on water distribution and water type systems, because that's the area that I work in, is trying to figure out how to build good water distribution systems and transmission systems in the face of all kinds of reliability issues and problems. So our main products in this area, well, we have, as you see on the screen, tons of different products to address water and wastewater and mapping and such. Focus on WaterCAD and water GEMS. GEMS is our top-of-the-line water distribution system model, and the G in GEMS stands for geospatial. So we're very much integrated between hydraulic analysis and the geospatial data community. We have tools that you can run our models within any kind of GIS software, as well as being able to run them as standalone. We basically, what we do is help with design and operation of water systems, and we do the hydraulic, water quality, and criticality kind of calculations. We have a lot of other tools, such as WaterCAD, which is our kind of entry-level water modeling system, SCADA Connect, to integrate with SCADA systems, and our transient flow analysis modeling, which is helpful because when pipes break, they also cause transient effects that can make the problem even worse. So the kind of things that we can help with are just helping to design systems for better reliability. And one of the most important things is where you place valves in distribution systems, because if you can isolate a problem to one city block, you're doing a great job. Places where things really go bad are when you have a pipe break, you see the picture there, and you can't isolate it to one place, and it spreads through and takes down a major portion of the system. We also have tools for fire flow analysis, for doing emergency planning drills to get ready for when the big earthquake happens, and response. During an emergency, you can be using our tools to try what-if things. What if we close these valves? What if we turn on this pump station? What if we turn off this pump station? And get good hydraulic analysis to help you with decision support. Just one quick example here. Let's look at a case where you're flowing water from the west side over to the east side of this slide, and you have a pipe break, let's say right about there. Looks like we've got a pretty reliable system. We should be able to isolate it. But if you don't design your system to isolate the pipe breaks very well and put in enough valves, you can end up in trouble. Same thing as if designing systems to get two feeds to the zone and find out that they're both in the same segment. So these are kind of tools that we have that can help you in planning for and responding to emergencies such as earthquakes. So with that, I'll thank you for giving me a few minutes to talk about our products and our technology, and I'll turn control back over to Talbot to introduce the folks from East Bay Mud on the forefront of this.
Thanks, Tom. That's really great. So that is a good lead-in to today's presentation. And again, our presenters are going to be Mr. Bouchard and Mr. McMullin at East Bay Municipal Utility District, and they're going to start in here on water system seismic fragility. Again, I remind everyone, first and foremost, hey, please join GITA. It's membership like yours that makes quality education like this for the geospatial industry possible. Simply visit www.gita.org and join now. Also, if you have questions during today's webinar, you have a look here at the upper right of your viewer. You'll see there's a chat window. You can open it up and fire a question off to me, and I'll make sure it gets answered by the end of the presentation. And again, just a reminder, please do turn off your volume on your phone, or mute it rather. And without further ado, Yogesh, Robert, take it away. It's all yours.
Thank you. Good morning. This is Yogesh and Robert here at East Bay Mud, and we're going to be discussing GIS applications, particularly on how you can use it as a tool to assess pipeline damage from liquefaction-induced settlements. This is two of us. The overview of our presentation would be give you a brief introduction on East Bay Mud, discuss some previous work that was done and damage models that were created for different stressing events, talk about the GIS-based liquefaction study, the CPT, which is cone penetrometer data, used to compute settlement and how the settlement varies spatially, discuss these results and then the impact to the pipelines, and then suggest some next steps on how to improve the robustness of our pipeline system. The East Bay Mud Water System, we provide drinking water for Alameda County and Contra Costa, 1.3 million customers in our service area. And our infrastructure consists of 4,200 miles of pipelines, 29 embankment dams, 147 tanks and reservoirs, and 331 square miles service area. And we have 1,800 employees that help keep our water system going. Some of the relevant publications I'm sharing here, you can access this. A lot of these were done some recently, one recently done in Portland, Oregon. And this, a lot of the work we are presenting here on liquefaction and use settlement was presented in a paper that we co-authored in Portland, Oregon Pipelines 2014. And we received very good feedback from that. And this is an ongoing body of work. So the question is, how do we prepare? We have had an extensive seismic improvement program, but permanent ground deformation causes the damage to pipelines and the permanent ground deformation. You have several damage prediction models. This cone that you're seeing is a bunch of input that goes in, which is a peak ground velocity, peak ground acceleration. Those are input metrics that you can get from essentially a big, large GIS database, which is from ShakeCast. It's by USGS. A lot of the stressing events are a function of the earthquake, the faulting, the sources, the distance from the source, and we put everything together and develop hazard maps for liquefaction, for landsliding, and for fault zones. All three of these mentioned can cause failure to pipelines. So we're showing some of the generic approaches towards coming up with site-specific damage to pipelines. So for our case, we have 29 embankment dams, 147 reservoirs, and we have a further breakdown of the types of reservoirs, and 360 miles of large diameter pipes. Well, now we have to start to break it down further into miles of steel, cast iron, reinforced concrete, and pretension. So that's a lot of data, and to manage all these different types of pipe, you really need to have some kind of an intelligent database, which is where we have built in a very large network of pipe, and all of our critical facilities mentioned here have their specific IDs within our GIS system. Well, we live in a high seismic environment. We show essentially the San Andreas Fault, Rogers Creek, Hayward Fault, and numerous faults. The red outline here essentially is our service zone for East Bay Mud. You will note that the Hayward Fault goes right through it. The working group, Bay Area Working Group, has developed a probability of 67% of the magnitude, 6.7 or greater from the years 27 to 2036. It's very likely that we will have an earthquake on the Hayward Fault. So knowing that, we need to try and mitigate against something that will happen. So there are many published scenario events, and we just tabulated these 6 scenario events, and Robert's going to get into the next set of slides describing the scenario events.
Okay, yeah, thank you everyone for attending our webinar. Once again, this is Robert McMullin from East Bay Mud, and one of the things we did here was for our damage prediction models for the embankment dams, tank reservoirs, and large diameter pipelines, we wanted to evaluate 6 separate scenario earthquake events. And before I get into this, can everyone hear me okay? Is this okay? Okay, they can't talk back. Well, I hope.
Yeah, you're doing just fine though.
Okay, yeah, thank you. I'm sitting a little bit of a distance from the speaker. But, okay, so we're looking at 6 scenario events that we used for our damage prediction model. 2 were from Brad Agard over at USGS, who was able to provide 2 Hayward Fault events that we could use, and they're provided with the abbreviations G1, G2. Then we were able to get 4 separate shake map scenario events from USGS website on www.shakemap.com. 3 of these are related to the Hayward Fault, 1 specific for the magnitude 7.05, and then we had 2 other ones that had varying directivity, being northwest or southeast. And these are represented by H3, 4, and 5. And then lastly, we wanted to look at the San Andreas fault line for the magnitude 7.9 event to see if those ground shaking velocities and accelerations would have any effect on our East Bay area. And that's represented by SA6. So to get into some GIS work here, Brad Agard, his data was provided in a grid format. So it was in the format of an XML. So we were able to feed this XML into GIS, and what's represented here are all these varying colors of square boxes. And this shows the intensities of peak ground acceleration, which was one of the input variables that we needed in order to calculate or predict damage. So with this, we were able to go through, identify the, we were able to show all the individual points where we had a PGA, and what we did here then is, based on where our facility lied, we were able to get an average peak ground acceleration based on where it was relative to the points surrounding it. So that was one of the GIS processes that we did in order to obtain a peak ground acceleration for each individual facility. And when I say facility here, that represents either an embankment dam, a tank reservoir, or a large diameter pipeline. Okay, moving on. The other data that we received from USGS Shake Map, this was easier to work with because it was in a polygon format. So with this, it was just basically a spatial overlay with our facilities, and wherever that facility fell into, we used that amount of peak ground acceleration. And just a reminder, this was for the Hayward magnitude 7.05 earthquake scenario event. Here is a figure, a GIS figure, showing all of the locations for our 29 embankment dams throughout the East Bay Mud service area. The East Bay Mud service area is shown in the black kind of shadowed region, and then you can see kind of San Francisco over to the southwest. These embankment dams are, you can see quite a few are located along the Hayward Fault line, which is a tough thing because they just have to be designed to take those ground shaking and ground movement design loads. Then once we ran through our damage prediction model, we were able to come up with where we had embankment dams that needed to have, if it went through our earthquake scenario events, this is where we could have varying levels of, not damage per se for this, but it's more where we would have to go out and check and assess the dams to see if there was any settlement at these locations. And as you can see here, we're getting results that make somewhat sense, and this is that we're having severe anticipated damage close to the Hayward Fault line, which is seen with the red crosses. We have light damage shown in yellow crosses, where I think we only had 1 or 2. Then minimal damage for the green. And this makes sense because most of our high ground shaking intensities will be in the fault line, and outside of that, those facilities won't see as much ground shaking, so they're not going to have as much anticipated damage.
And just to clarify, I know it says minimal, light, severe. Those are more classifications, but it's more a performance criteria. So, like as we mentioned, if it's severe, then it just means we expect all of even the ones that perform at a severe damage level will not undergo anywhere near failure, and all of these dams have been checked by Division of Safety of Dams for the scenario shaking event. So it's more an emergency response type tagging.
Yeah, for sending our crews out to just assess to see if there's any kind of repair work that would be required. Okay, so moving on, we looked at dams, and we also looked at tank reservoirs. So this GIS figure shows the 147 tank reservoirs throughout our East Bay Mud service area. And in this area, you can see that most of our reservoirs are east of the Hayward Fault, and that's because that's where we have the higher elevations, and this provides our pressure or head for providing a pressurized water system to our customers. And as you can see, too, we have quite a few tank reservoirs along the Hayward Fault, which we would anticipate to have some expected level of damage when the Hayward Fault earthquake scenario was reviewed. Here, this shows our results. This is the anticipated level of damage based on reviewing the 6 scenario earthquake events. And as you can see, there are a few extensive damaged reservoirs, and they're shown in orange on the screen, in orange triangle. Then we have moderate damage shown in yellow triangle, and then green shown, the green triangle shows no or slight or minor damage. With this, the extensive damaged reservoirs, I think were wood reservoirs, so depending on the type of characteristics for each reservoir, they wouldn't be able to have the same tolerance level for ground shaking as, say, a steel reservoir. That's why you see a couple reservoirs located right along the Hayward Fault that still have no slight or minor damage associated with that. Okay, so moving on to pipelines. This was my bread and butter for the review of the project. And when we went through the damage prediction, we only wanted to look at kind of like our large diameter pipelines or our transmission mains, and we wanted to define this such where we wanted to look at 16-inch cast iron pipes and then 20-inch diameter for all the other pipe types within our system, and that includes steel, reinforced concrete cylinder pipe, pre-tension concrete cylinder pipe, and then high-density polyethylene pipe, or HDPE. For this, we wanted to look at smaller diameter cast iron pipes because we've had some recent damage on our larger cast iron pipes, and we just wanted to include it in the system to see if they popped out when we reviewed damage prediction. So this shows a GIS figure of our service area with all of our varying large diameter pipelines. So we had 360 miles as stated earlier, and they're divided up as cast iron pipe shown in kind of like that purplish color, green as the pre-tension concrete cylinder pipe, kind of a beige as the reinforced concrete cylinder pipe, and then we have a lighter blue for the steel pipe. As you can see, the breakdown of this is that I think approximately like 80% of our system for large diameter pipes are steel, and then it's a breakdown of there between cast iron, RCCP, and pre-tension concrete cylinder pipe. And something to note on this is that in the west of the Hayward Fault Zone, this is called our West of Hills area, and it's the area that lies along the bay. So that's where we have different varying artificial fill soil types, where Yogesh will get more into this later on. So that's where we would expect to see quite a bit of damage based on any kind of ground settlement. So one of the ways that we did all of these GIS processes, because we're dealing with a polyline here, it's a little bit difficult to determine where or what type of ground shaking intensity was seen on the pipeline, because a polyline could pass through multiple ground shaking intensities. So what we did here is we took our polyline and then we broke it up into 1,000-foot segments or points, and each one of these individual points would represent a 1,000-foot segment. So this would be much easier to model and be able to do spatial overlays to get a sense of how the ground shaking intensity would vary spatially along the pipeline. And then here shows the results. Our 360 miles of large diameter pipe have now been converted into 1,891 individual pipe points. When going through the different scenario events, this shows where we have potential for damage, and this is for landslide. So all of the red points, that shows where we could have potential landslide damage based on the spatial ground shaking intensity, and then also based on the type of pipe, because certain pipes may be more sensitive to damage based on ground settlement because they may not be a rigid pipe or have a rigid joint connection. And this would be our reinforced concrete cylinder pipes and our cast iron pipes, where they're just pushed on. So any kind of movement would create a disturbance and would be able to pull out a joint, and that would be considered a leak or a damaged pipe after an earthquake event. Moving on, here is our fault summary, and as you can see, for the Hayward faults that we looked at kind of the worst case scenario, which was almost a 7.05 magnitude event. And with this type of an event, we're likely to see upwards of 5 feet along the Hayward fault. So that's where you see a lot of these points are showing up as anticipated damage, or red, along the Hayward fault line. Okay, and then lastly, we also looked at liquefaction. And this is where we used current USGS liquefaction data, and we were able to determine where, based on the soil type and other parameters, we could see or come up with an estimated level of settlement and compare that to the pipe type and see if we would be able to, if that would exceed the strength of either the pipe, or for the unrigid joints would exceed the level of settlement that would cause a pullout or break along the pipeline. So here, all the red points show where we have anticipated damage. And something to note on this is that they're all in the west of hills area, and it's due to our soils along the bay. And Yogesh will get into more detail on this right now.
So, primary cause of settlement is liquefaction. Liquefaction is essentially a process where you have loose saturated soils that change their state from solid to semi-fluid due to pore pressure increase. So a lot of research has been done in this area, as we mentioned, all the artificial fills in Oakland and west in Alameda and some of the maritime. We'll get into the geologic formations. So the past work we had done in landsliding and liquefaction, we felt was not robust enough, particularly for liquefaction, since that is a major trigger or cause of pipe damage. And we've noticed from Loma Prieta, we've noticed also from recent Napa earthquake, from the 1906 earthquake, and the list goes on in China. And so in Turkey, Japan earthquake, a lot of wharf structures, a lot of pipelines get damaged. And this also is a concern in San Francisco, where you have a lot of the fills that are anywhere from 40 to 400 feet back from the pier structure, and the northern seawall, which the port is looking at now very closely. So this is a major concern on utilities, on buried utilities, because they will just essentially move with the ground. So there are two types of liquefaction. We're looking at like settlement, and we're not looking at lateral spreading. So following these slides, I'm going to just kind of skim over the geotechnical issues. The liquefaction aspect of and settlement and computations are pretty detailed, but this is more of a talk on the results and how it impacts the GIS and where the pipes intersect. So these essentially showing the cast iron and the different types of pipes, steel pipes. You see, we have, this is the Alameda, this is the Western Oakland. A lot of these areas have artificial fills. Those are of concern. And Roberts mentioned the 1891 points to define the pipes. Those are shown there. So components of this calculations for liquefaction, shake map scenario, we have a previously mentioned the Hayward magnitude 7.25 earthquake, PGA and the peak ground acceleration, that is. Those are some of the one of the main input metrics to compute liquefaction, among many other parameters. USGS data. All those dots you see here are complements of United States USGS. A lot of the CPT, cone penetrometer test data, I'll explain later briefly, is available on the USGS site, and you can come up with these computations using different analytical tools. This is a CPT test. This is our this is a rig, and on the right here you see photographs of the cone. This is like a 60-degree angle here at the tip, and you measure the tip resistance and you measure the sleeve friction, and you use those two pieces of information. Those values are in stress, and here's just a quick cutout. The bottom you see the cone. You have a load cell. It measures how much tip you're what stress you're measuring at the cone, what stress you're measuring along the sleeve friction. And this rod is pushed into the ground by that truck you saw earlier, and it's pushed at like a constant rate. Anyway, just skimming through all this the stuff, you have this QT, which is the tip, F is the sleeve friction, and then you do a bunch of geotechnical number crunching, and come up with this soil behavior type. And here's soil liquefaction during earthquakes. Just want to give this reference. Professor Idris and Boulanger from UC Davis. Now I went there, and Greg Drilling are the guys that did a lot of the CPT. We worked very closely with also PK Robertson, who has helped with our CPT study. What we're after is settlement at the ground surface, because pipes are near ground surface, relatively speaking. So you have these values. You have this artificial fill, which is very typical of the Alameda, Oakland area, for example. And then you have maybe the silty sand. I'm showing a very generic profile. And you have settlement on the x-axis here and depth here. So each point you saw has this characteristic curve. And the magnitude of settlement increases as you go to the ground surface. So it is cumulative. So the pipe at the top, this is in meters, the pipe at the ground surface, which is let's say 3 or 4 feet below, will see the maximum settlement. And as you get further and further down, the cumulative settlement drops down. So that's all we're trying to show with this plot. So every one of those dots we showed earlier, we did a settlement calculation on. Okay. Now we had mentioned the input metrics, the PGA, and we had shown the gridded areas where you can extract PGA acceleration values from, and those are all within GIS. Okay. And then we have to come up with this kind of relationship. The settlement at the ground surface is very much dependent on how much acceleration you will feel at the site at that particular sounding. The CPT is called sounding. So the greater the peak ground acceleration, the greater the settlement. And so this is all that these are just different analytical tools that geotech may be interested in, but maybe if you're GIS, you're not so interested in this topic. But believe me, this kind of geotech spend days and years and months just on this topic. So, but I will spare you the agony. So USGS Tom Holzer of USGS has done great work in this area and really acknowledges his compilation of work that he has done so far. We heavily relied on his work. So he has come up with the LP, a liquefaction potential index, and the percentage, the probability of liquefaction in zones in artificial fill over here in Oakland, Alameda, and West Oakland is very high, 73%. So it'll liquefy. Well, this is good, but we really need to come up with how much settlement you will experience at the site. Okay, so those are all the dots. Those are 212. Analyzing 212 CPTs is very time-consuming, and Mario, our intern, and Kevin, who was an intern at East Bay Mud, and now Ryan Little has been helping us do a bunch of number crunching. So that's the surface zone. We analyzed all 212 CPTs. We did settlement calcs using 3 different methods for 10 different range of peak ground acceleration, and came up with different fragility curves for settlement and PGA for each one of those points. That took a lot of work. But so I'm just superimposing the artificial fill, which you see, which again mentioned in Alameda area, and we'll superimpose the pipelines very soon. These Holocene alluvial fan deposits, all these boundary layers are clearly identified in GIS. And the Merritt sands, which is here, and those are the artificial fill areas. Okay. So the settlement estimates, we had to pick a PGA number. We picked 0.5. Okay, that can be debated, but that's a pretty good number. So we stuck with that number. We came up with settlement magnitudes at each of those soundings for that PGA metrics. Those values you see are in centimeters, 8.84, for example, in this, well, I'm calling this 1, and then I'm calling this 2. So we went through, and in GIS, we said this, we cut the boundary of the Merritt sand, we cut the boundary for this artificial fill. Now, pipelines that, so we came up with a bunch of statistical minimum values, maximum average values for these small number of soundings. This is a very small number of soundings for the given the area for geotechnical characterization and settlement. So we had to use a lot of judgment. Then we cut all the results of the soundings in this area, meaning the Alameda fill area, and we did averaging there because those were higher in magnitude than the settlement magnitudes in area 1. So it's very critical to break down these areas based on space, based on geologic formation, based on soil type and geologic formation. Then it gives us a more realistic idea of how much settlement will occur within that zone and in between that zone at the intersection of those zones. So that's why this slide is showing the liquefaction settlement and broken up into zones 1, 2, 3, 4. Those essentially, like for example, 2, 3, and 12 would be the artificial fill. Okay. So now we need to take min and the average and the max value curves and run some fragility analysis. We have to compare what's going to happen. Now just superimpose all these, the pipe network. Okay. The distribution less than 20 inch, transmission 20 inches and greater in shown in red. So we can do this in GIS. Then what we can do is say, well, all these pipes that go through this 1, which is the Merritt sand, and then 2, artificial fill, we expect to see high settlement in this area and fairly high settlement, and low settlement up in the hills. Obviously, there's no liquefaction there. So what happens to the pipe that goes across these boundaries? And the pipes that go within the area 2, those will see maximum stress. So let's zoom in. So now we're zooming in and looking at settlements in these different areas. I'm showing essentially a window. You see values 4, 3, 11, 6, and then you see 9, 16, 20, 18 centimeters in the zone 3, which is artificial fill zone. And so we want to look at that a little bit. So you have this zone here. You have a scale map. We just zoomed in. And if you look at like an intersecting boundary of artificial fill to the Merritt sand, that width is about 100 feet. Now any pipe intersecting that would be subject to the differential settlement. And
to give kind of an outlook on what GIS process was done here is we basically just ran a 100-foot buffer around the boundary area between these liquefaction settlement zones 3 and 4. And with that, we were able to go through and select the pipelines that had or that intersected this buffer line, because this is where we anticipate to see the greatest level of differential settlement and would anticipate to see the most amount of damage on pipelines. And then this shows our buffer that we created that was approximately like 100 feet. And what we wanted to do here is just to select the pipelines that crossed. looking at this pipeline, we were able to identify that we had a crossing, and this was 24-inch diameter welded steel that was installed in 1966, and we were able to look up the attribute information regarding it. So we were able to see its steel, when it was constructed, and other various characteristic information that we could use to assess if this pipeline would damage based on the varying levels of differential settlement that Yogesh will get into in a little bit. Then we also have another crossing in kind of the eastern part, which is another 24-inch welded steel pipe, but this one was a little bit newer, which was installed in 1996. We could also look up the attribute information on this, so we could understand the characteristics of the pipeline that crosses this liquefaction boundary line. And with this, we could assess whether or not that pipeline would be able to withstand that level of differential settlement.
And so just going down into the Alameda to show you that this is actually one of the areas that had the greatest differential settlement. And for example, area 1 and 2, and then Roberts superimposed the pipe network through here, and we were able to zoom in on this area, and you see, 7 and 2.8, and then you have higher settlement magnitudes in the blue is artificial fill, and that's our 100-foot zone.
Yeah, and then once again we ran this the buffer line between the zone 2 and 1 and 2 because we would know that this would be the greatest amount of differential settlement. So with this, because we were only focusing on transmission mains or larger diameter pipes, I know we have it listed here as 20 inches and greater, but we also looked at the 16-inch and greater for cast iron, as noted earlier. So we overlaid our pipeline network with these liquefaction boundaries, and we're able to come up with this buffer line, understand what large diameter pipelines have an intersection, and then we were able to identify that. And here is another 24-inch diameter. And now this is a little bit, it's an older steel pipe because it has riveted steel connections, and it was installed in 1947. So with that, we were able to look up the attribute information, again, based on that pipeline, to further assess to see if this pipeline would be able to withstand the greater liquefaction displacement between the two zones 1 and 2.
So the key is here, what is the settlement that the pipeline is going to experience, and then what is the maximum differential settlement, because pipelines don't break if the settlement and the curvature of the pipeline is below the tolerable elastic strain values or below the bending stress values. But when you have an abrupt change, or in pipeline terminology it's called PGD, or permanent ground deformation, which could be from liquefaction, lateral spreading, or landsliding, or fault crossing. So in this case, we feel that the most abrupt would be at the boundary layers, and it's not more than a feeling. It's actually based on our settlement calculations. So here now we're starting to look at relative settlements of the two intersecting boundaries, 1 and 2, which we refer to in this artificial fill and the merit end. So you are getting 20 inches of settlement, in centimeters, 20 centimeters of settlement at the 0.5 G, peak ground acceleration of 0.5 G. And that's a high estimate, and we can go over the logic of the low, average, and high, but using a high value is actually would not be considered so conservative given the spatial distribution of the data available. And some might argue that you should use that as an average. So it's not far from reality to see a 20 centimeters of settlement, but what is it over what distance? And you can argue that could be a small distance, say 20 feet or 50 feet, or so that is another question to be answered. So the ranges would be anywhere from 6 to 13 to 25. Then if you look at relative settlement, so all these curves, there's quite a bit of work that has gone behind this to develop the relative settlement curves versus PGA. This is 3 versus 4. So if your pipeline is in the Oakland area, which I mentioned 3 and 4 earlier in the maps, artificial and merit sand, the difference between the two could be like 10 centimeters. That's quite a bit. Then another curve, 3 versus 5, and then we have actually developed a full suite of curves, which for all the layers that overlap, or sorry, that a pipe would intersect or go across. There's a question of how does it go across? Is it perpendicular to the intersection line? Is it actually parallel? So that requires some judgment and some thinking and some logic that could be built into an intelligent GIS system in the future. Well, what does it mean? We have these relative settlement values we're showing you here versus PGA. So how does it impact the pipe? So here's a cartoon figure. There's L is the hypothetical length, could be, as I mentioned, 20, 30, 40, or 100 feet. Then you have a certain amount of deflection, which you're showing in the delta. And without going into this equation, this essentially shows how we computed a very simple loading on a pipeline for different span lengths and for different deflection values. Well, we have the deflection values from the intersecting boundaries. So can we then create a bunch of curves here that compute the bending stress in the pipe for the different deflection values? So, sorry, we're switching to inches here, but I'm showing you deflection in inches along the x-axis, and this is for a very typical pipe in Oakland, Alameda. It's a 22-inch, and it has a thickness of 3/8 inch. And then we're looking at these horizontal lines essentially are the allowable bending stress, and then the red line is the yield bending stress. Performance criteria could be either or. One could argue that you should look at the yield to be less conservative, but that's something that we need to go through and make a philosophical decision on. For example, this the middle one, which is a 40-foot span. You have a 40-foot span. If the deflection is 8 inches, which is quite possible, we showed you 22 centimeters earlier, which is close enough, you will exceed the yield bending stress. And this is the same plot, without getting into much detail, this is the same plot essentially, but instead of stress, we're looking at strain. So the same type of pipe. So again, for a 40-foot span, which is not that's a very reasonable number in terms of span lengths across liquefiable boundaries. So it is quite possible to exceed bending strain.
Gentlemen, not to be rude, just to give you a few more minutes to wrap it up so we leave time for questions.
Perfect. We just have 2 more slides. And then to see, well, okay, great, you're exceeding bending stress and bending strains for 8 inches. What are some mitigations? We can look at something simple. Of course, you can have flexible connections, or you can increase the thickness of the wall for the pipes. That would increase the the allowable the amount of deflection that these could take before they would yield. So this is just a quick plot of what is possible for the different thicknesses of steel for a 50-foot span. And this is the next step that we could feed back into our GIS database in terms of being able to develop this a table that is extracted from GIS, run these bending moment and deflection curves, and then maybe have GIS recommend areas that should be thickened, where pipeline should be thickened. So with that, that's kind of the end of the presentation, and we'll be glad to take any questions.
Thank you very much. That was an excellent presentation. Again, if anybody has some questions, please pop them into the chat box here, and I'll make sure that they get asked. One of the ones that's popped up here is the idea of cascading infrastructure failure, you were showing some pretty detailed maps of where pipes may and may not fail. Is there anything you do to carry that like one step beyond East Bay Mud to say, okay, dear hospital or dear fire station, we've done a vulnerability analysis and we know the main in front of your fire station is going to break if the peak ground acceleration exceeds this. If so, you may want to put your fire truck in the parking lot next door or something like that. So have you explored any of that?
Yes.
Yes.
It's interesting. We're in the process right now where we're working with someone from the University of Denver, and then someone also at USGS, where we're evaluating lifelines. So we're looking at all different types of utilities, and then all different types of kind of shelter, hospitals, and other kind of critical facilities, and what facilities need to stay in power or to have water after like an earthquake event. So yeah, we are in talks with giving this information on to other groups so that they're aware of where we may have sensitive areas that may need to have after an earthquake event to have our crews go out faster to make repairs, or when we do replacements in the future, we'll know that it's a sensitive area so we can make the new pipe that much more resistant to settlement.
Another question here that's popped in is, what are the plans for closing valves to isolate breaks quickly to prevent water loss, flooding, and low fire flow?
Yeah, with this is a great question. It goes back to Tom's presentation beforehand, where you need to be able to isolate these lines so that you don't have a major catastrophic loss, similar to what was seen down in LA at the UCLA campus, which was very unfortunate. One of the things that we do is with our design standards, we try to put, for large diameter pipelines, we put in valves every, say, like 2,000 feet or so. And that may seem like a lot, but for these large diameter pipelines, they're hopefully designed such that they shouldn't have any kind of excessive break, but when they do, we need to have these valves put in place. The other thing with this is that this is hugely weighted upon having a great maintenance crew, because you need to go out and make sure that these valves actually work. And that's one of the problems that can happen for any agency, where you may have a 50-year, 60-year-old valve in place and it hasn't really been worked or exercised in so long. So it could be, if you do have a critical pipe break, that when you go out there to close the valve, that the valve may not even be able to close, and then you have to go to the next one down. So it could be potentially 4,000 feet away, which is upwards to a mile. So it's quite a bit of water loss and damage that could be seen. So yeah, this is a very critical thing that we look at, and whenever we do new pipeline designs, we always try to put valves in at key locations so we know that we can isolate.
Any thought in tying that type of valve works to your SCADA system so that they can be automatically closed?
I think we do have those on specific valves, but within kind of our, I think in our distribution, kind of in the treated water system, I don't know if we have any of those. I think we may have some seismic active valves where as soon as we understand that there's been ground shaking that exceeds a certain level, that these valves go into motion where the actuators start working, and it has like 20 minutes to a half an hour sequence to close the valve. That's all we have at this point.
Okay. Absent any more questions, we thank you very much for all this fantastic information. Again, this webinar has been recorded and will be posted to the GIT website and available for free to all. We especially want to thank our corporate member sponsor, Bentley, and Tom for doing an excellent overview of their capabilities. And please tune in next month. We'll have a discussion about the collection of municipal address and structure data for preparation and mitigation in crisis response, and a case study with the recent Winstonville tornado. I know we kind of seem to have a disaster focus right now. It just seems to be one of the topical areas that folks are expressing a lot of interest in. For those of you listening, we do encourage you to please submit your webinar ideas to us, and either you're welcome to present, and if you're not interested in presenting but want to hear about a particular topic, let us know and we'll find somebody to talk about something. And keep an eye on our newsletter, the News Hub. If you're not signed up, you can do that on our webpage at the lower left-hand corner as well. We'll continue to announce our webinars there and try to bring you the latest in what's happening in industry. That concludes today's webinar. And again, thank you very much for your time and attention, and we look forward to hearing from you in the future.
Thank you.